Last week, part 2 of our general relativity series went a little deeper into some aspects of flat space-time geometry. I said some unfamiliar things, and it got a little intense, so just like after part 1, there was some confusion. I answered some of your questions on the comments page, but there's more that I'd like to clarify today before we move on to part 3. In a minute. First, I have a pretty important announcement. I'm sad to say that I'm stepping down as the writer and host of PBS Spacetime. This fall, I'll be starting full-time work at the U.S. National Science Foundation, and while I'd love to keep doing Spacetime, I just won't have the time to do it right. Now don't worry, Spacetime will continue. It has to. It's the basis of all reality. And we're looking for a worthy new host to keep that dream alive. And we think we found one. Maybe. I personally will be doing 3 more full episodes after this one, plus one final challenge question, a little harder than normal. Keep an eye out for it in a few weeks. You can also always keep in touch with me on Twitter. I'm at PhysicsGabe. But sometime in August, I'm going to hand over the reins, and I'll be doing so with mixed emotions. For me, doing the show has been an awesome experience, and I'm really proud of how far the show has come. I never thought that I'd be part of a production that has almost 100,000 YouTube subscribers and 2.5 million views. And it's all thanks to you guys. I mean, without question, Spacetime has one of the most curious, most cerebral, and best behaved audiences on YouTube. And I think that our content and you guys, the audience, will continue to raise the bar even higher. Interacting with you has been, for me, the best part of doing the show, answering your questions, hearing your comments. So you've made this whole enterprise possible and rewarding, and you've really taught me a lot. So I'm just going to end by saying thanks to all of you. Okay, let's do some space-time questions. A lot of you left comments saying that you were totally confused or felt really stupid watching this episode. Look, welcome to my life. That's what studying physics is like when you're trying to do it at any depth, even if you're not yet getting into the math. This video that we made was not intended to be digested in 10 minutes. It's hard stuff, and the idea is for it to sink in over multiple viewings as preparation for what we're doing next week, which I promise will be less intense. But as John Baluba and Aditya Mokarala pointed out, after you view it a second time, it starts to make more sense, and by the 3rd or 4th, even more. So be patient, hang in there, you'll get it. And as a corollary to this, you should go back and look at the comments page on the original YouTube video and read it. If you have a question, a lot of other people have probably asked the same question. It can save you time if you look at the answers that I've already given that person, and then you can go from there. But by all means, don't sell yourself short. Just read all the information that's in there. There's a lot. Then group 2 asked a question that's actually going to be important for next week. He asked whether the inertial frames that I discussed in the episode are the same frames that we would ordinarily see moving with a constant 3-dimensional velocity through space. And the answer is yes. Inertial observers will see each other dynamically moving with a constant 3-dimensional velocity. But does that mean that inertial observers are really moving with a constant 3-dimensional velocity? Remember, in Newtonian physics, there's no unambiguous answer to that question because you can only talk about motion relative to other things. What the space-time picture, the flat space-time picture tells you is that in a world without gravity, there's a way to discern who's really moving at constant 3-dimensional velocity, sort of, which is those observers whose world lines in space-time are straight, i.e. that are geodesics of space-time. Those are the guys that it turns out correspond to inertial observers in Newtonian physics, and they are distinguishable from non-inertial observers in a geometric way in spacetime. Pifrock from France corrected my French and also corrected an error that we had made in the space-time diagrams that we showed at minute 5:04 in the video. Some of the dots that we had placed in the 2 red guy and blue guy space-time diagrams were placed inconsistently. We've produced corrected versions of those graphs that I'm going to show you in a second. They're going to stay on the screen for a few seconds, and then we're going to add an annotation and a link in the original video that will take you over here to see the corrected things, just so everything is self-contained. Finally, Tommy Taffy and Dan Fox asked a question that's really pertinent to what we're doing in part 3. Namely, how would everything have looked from the frame of reference of the accelerating car? Dan Fox in particular asked whether the accelerating car's own world line, wouldn't that look straight from the car's frame of reference? I mean, it would. But here's what's tricky. It is tricky to talk about the car's frame of reference in special relativity. It's not impossible, it's just extremely awkward and very, very cumbersome. You'll notice that all the space-time diagrams that I drew in the last episode were from the point of view of inertial observers. Blue Gabe, Red Gabe, the pony, all of them were inertial. They're moving at constant spatial velocity. If you try to draw the accelerating car's frame of reference, things get really messy. And this is part of what prompted Einstein to want to develop a more general way of talking about the world that would work for any frame of reference, including the accelerating cars. But here's a preview of something that we're going to do next week that I want you to start chewing over. Imagine a family of inertial observers, all of whom are moving with different speeds relative to each other. That accelerating car at any given moment from its point of view is always stationary instantaneously relative to one of those inertial observers. So even if we can't talk about the accelerating car's entire frame of reference, we can talk about a sequence of inertial frames of reference relative to which at any given moment the car is instantaneously stationary. And it might be the case that by stitching together all of those points of view, the accelerating car might be able to develop a self-consistent picture of the world. Think about it. Okay, I hope I gave you guys a little bit more clarity on this last episode. Think about all these things. You have another week now before we dive into part 3, curved spacetime, and finally an explanation of Einstein's self-consistent view of what gravity isn't. See you next week on Spacetime.